Look around the world beyond us. Can you believe you already see the reality? Or there were things we can't still understand? Just like a puzzle that we still need to solve. This video will give a short understanding about quantum mechanics, the development of quantum theory, and its relatedness to chemistry.
Atoms are the basic unit of matter and defining structures of elements. The term atoms comes from the Greek word for indivisible, because it was once thought that atoms are the smallest things on the universe and could not be divided. We now know that atoms are made up of three particles, such as protons, neutrons, and electrons, which are composed of even smaller particles, such as quarks. So now, let's draw the atomic model of Niels Bohr. These are the atomic model of Niels Bohr. Black body radiation and Planck's equation. One of the first ideas proposed to set quantum mechanics apart from classical physics was Max Planck's idea that energy like matter was discontinuous. This revolutionary idea stemmed from black body radiation. A black body radiation is an object that absorbs all the radiation falling on it. An object that absorbs all the radiation can also perfectly emit all the radiation. Therefore, a black body will radiate a maximum energy when heated to a given temperature. Under the classical physics, this energy emitted was predicted to be infinite. However, when it didn't radiate energy indefinitely, scientists were faced with the problem of explaining the phenomenon. This leads to Max Planck's proposed idea that unlike classical physics, quantum theory limits to a set of specific values. Each of these values isn't continuous, but rather increases from one allowed values to another by a small or quantum. More specifically, a quantum is the difference between two allowed values in a set.
Based on the assumption that all atoms on the surface of the heated solid vibrate at the frequency, Planck developed a model that came to be known as Planck's equation. Through experiment of frequency and temperature, Planck was able to generate a constant. It was called Planck's constant, where h is equal to 6.62607 times 10 to the power of negative 34 joules. Using this constant, he was able to restate his theory. Energy was directly proportional to frequency. He wrote his equation as E is equal to h times V, where E is energy, h is Planck's constant, and V is frequency. However, due to lack of solid proof, scientists including Planck were skeptical about the new field of quantum theory, since Planck's hypothesis couldn't be applied to anything other than black body radiation. It wasn't accepted until much later when it was successfully applied to other phenomena.
The photoelectric effect. The basic idea behind the photoelectric effect is that under a certain condition, when light is shined on a sample, electrons are ejected from that sample. Experimentation show that the frequency of the light has to be above a certain threshold values for electrons to be emitted. After studying the photoelectric effect under several conditions, scientists made three observations. First, a certain minimum frequency is required for electrons to be emitted. Second, kinetic energy is directly proportional to frequency. The third, the number of electrons emitted from the surface was not dependent on intensity.
Scientists realized that frequency, not intensity, controlled whether or not electrons were emitted. Under classical wave theory, electrons would be ejected at any frequency as long as it was intense enough. But this doesn't happen. Since this dependency on frequency couldn't be classical physics, scientists had to turn to quantum theory. In order to explain this effect, Albert Einstein proposed that electromagnetic radiation also had particle-like qualities. Each of these particles of light was called a photon. Einstein suggested that each photon has an energy equal to hv, which is called a quantum of energy. This quantum of energy is the energy that is required of each electron in order to leave the metal surface. A light of smaller frequency cannot eject an electron no matter how long it falls on the metal surface. The reason the photoelectric effect was so significant was the relationship between radiation and particle of matter caused scientists to understand that the wave theory of radiation wasn't going to be enough to explain a lot of phenomena. This leads to the development of a new way of thinking, wave-particle duality.
Ideas that lead to quantum theory. One important idea that is the basis of quantum theory is a wave-particle duality, first shown through photoelectric effect. In order to prove that the electron was wave, G.P. Thomson designed an experiment, the double-slit experiment. When a stream of electrons was directed at metal fall through one slit, a thin band was formed on the fall as expected. Likewise, when the electrons were directed through two slits, two bands would be expected to form. However, the experiment showed that an interference pattern, like would be expected of a wave, was formed instead. This experiment was one of the several that gave rise to quantum mechanics.
This is an example of another separate rule for quantum mechanics. In the microscopic world of classical theory, a wave is a wave and a particle is a particle. One cannot and will not never be the other. However, in the microscopic quantum world, this isn't true. Electrons of atoms and photons of light aren't necessarily particles or wave. In fact, physicists are having a hard time determining just what they are since they have the properties of both waves and particles. Another important idea in the field of quantum mechanics is the Heisenberg uncertainty principle. From a broad perspective, the uncertainty principle states that the position and momentum of a particle can never be precisely measured simultaneously. If one is known, the other cannot be determined accurately. This principle is a consequence of wave-particle duality and therefore leads physicists to embrace a modern descriptions of atom.
Now that you have already gained an overview about quantum mechanics, you might be asking, do I really need to know the right structure of atoms? The answer is this. We might not be able to reach this level of technological advancement without that knowledge. We might not be able to develop new inventions that have brought us to a graded and more advanced society. Our knowledge about the behavior of atoms have helped us a lot in fields of medicine, physics, engineering, chemistry, astronomy, biology, and lots more. So, are you now prepared to level up more your understanding about the world beyond us?